So, right, this is the slide on the screen there is one of SOM's projects. What's his name? William Baker, is a very enthusiastic supporter or proponent of this GraphicStatics as a design method. He kind of came across it, a decade or so ago, and realized the potential in terms of design. So this building that's on the screen was actually the truss work on the exterior was designed with this method, with this GraphicStatics. So it's I mean, there are other ways you could do the same thing, but it's kind of an interesting technique to combine the forces and an actual picture of the forces and be able to manipulate. Well, it's like a duo. You can manipulate the forces and see the change it makes in the truss, or manipulate the truss and see the change it makes in the forces, and kind of understand the action of the forces a little bit better like that. Okay, so I think I can close that. See if I've got everything except the thing on the screen too. I can't change slides. Let's see if we can do it like, maybe I can do it like this. No. Okay. Okay, now I went to let's see where my slide control went. Ah, man. Seems so difficult sometimes. You get 3 different images and I can't get the image I need. Okay. And I don't have... Oh, here we go. There we go. Okay, so you can control it like that. So it has a long history. James Clerk Maxwell, I guess, was one of the first people who worked on it. But you can see there was a lot of development rather rapidly in the late 1800s. He kind of proposed it. Willett and Moore worked together. There's a method called the Willett-Moore method that is pretty much what we follow. Cremona added a few, I guess, techniques to it, but so sometimes they're called Cremona diagrams. You'll see them referred to by those names. The Willett-Moore diagrams is the way I learned it, or Cremona diagrams. Later, Heinrich Müller-Breslau, who you may know from, what else did he do? Influence lines. If you've ever worked with those, Müller-Breslau worked on that graphic technique as well. So there was a lot of, this was, of course, before the advent of computers, before the advent of calculator. I don't know, when did, I think they already had slide rules by late 1800s, but about that time. At any rate, you were rather limited in your ways you might calculate a truss, so doing it graphically was certainly a reasonable option. And it continued, this technique, through the 20th century up until, I mean, even, I think I'm the generation where it just about disappeared. When I was in school, like you are now, my textbook had a chapter on GraphicStatics. We had, let's see, what do you use now here? You use Hibbler, don't you? And we had what's his name? McCormick, Jack McCormick. If you've ever seen, he has a very good statics book. Jack McCormick, by the way, have you ever had any textbooks with him? He is an excellent author. He's down in Clemson and has written textbooks on concrete, steel, and there's one on just general mechanics and strength of materials. And he's just a very good, I think, a very good author. When I was your age, I actually started teaching in the School of Architecture before I had my engineering degree. So I was simultaneously teaching the basic fundamental structures courses and then taking engineering over in the engineering department, the courses. So yeah, I was very incentivized to learn it very well. And when I'd start a new subject, like in steel, for example, I took a course on steel. So I went over to the library and got almost every textbook there was on steel. And I laid them all out on my desk, and I'd read it, the chapter in this one, the chapter in this one, the chapter in this one, the chapter in this one. And I'd go through all of them, and, Solomon and Johnson, he's a Greffen, there's one that begins with a Greffenstedt or something, I forget his name. And McCormick's always had the easiest to understand, the clearest, and I thought the best explanation of things, very concise, but very to the point, and explain how to do it. So I fell in love with Jack McCormick's books. Anyway, you should check him out sometime. He's pretty much retired now, but the books I think are still kept up to date. Anyway, so I was kind of about the end of it. I can imagine in Hibbler, there's not if that's who you guys had, there's not a chapter in GraphicStatics. I think that's a newer book, and it's probably just past it. We didn't really use graphic. It was like in the book still, but we didn't really learn it. So that's why I said I'm kind of the generation where it disappeared. In the post-war, the 50s and 60s, they probably still had that. I was going through school in the 70s and 80s, so it was gone. So that was about where it disappeared. But then in the a little bit later, in the 90s, it made a comeback, and it's because of the discovery of its application to design. And these are the people that really promoted it. MIT, Oxendorf, and Caitlin Mueller are both big advocates of it. I think Oxendorf was probably one of the first people who really pushed it. Caitlin is his student, and Philippe Bloch is also a student of Oxendorf's. Philippe Bloch is in the ETH in Zurich, and he works a lot with vaults and what do you call them? Gravity arches and gravity vaults, catenary vaults and arches, and those are also done with GraphicStatics. Can be. William Baker then, through an association with these people, also picked up on it, and he was in a position really to realize some big projects. If you don't know him, he came and spoke here, I believe, a few years ago, didn't he? Didn't Bill Baker come? Anyway, he's the head of engineering at SOM. So he was involved in a lot of big projects where it could be applied. At any rate, I'll post some paper. If you're curious about it, you can look through some of the papers that these people have published that describe how you use it in design, or how they've used it as a design tool. But what we'll do first here now is go through the I'm just looking at my thing. I hope this is recording the right screen. Yeah, I hope so. It was set up to do it right. Anyway, we'll go through the steps and how to do it. First, we'll go through how to analyze a truss using this method. That's pretty straightforward. And then what you do is you do it backwards to design a truss. So the idea, the reason this works so nicely, trusses are two-force systems, right? They're axially loaded, and the direction of the forces is exactly the same as the direction of the members. So there's a direct relationship there between the forces and the geometry that they're in the truss itself follows the direction of the forces. So you can graph the forces using the geometry of the truss. Okay, so there's a little procedure, and it makes it easier. You can do this in different ways. Like the Müller-Breslau uses a little bit different numbering system than Cremola, so there are different ways to do it. You can see, but this is one pattern, and if you follow it, you come to the solution pretty easily. So you start with the truss, okay, with the load. Whoops. Okay, you know what? I don't think I even have this on. Okay, you start with the truss, and you draw a simple diagram of it to scale, like on that graph paper or something. And then you take that and number it, first you letter the exterior panels. So what you're lettering are the spaces outside the truss and the spaces between the external loads. So I've got a load there and a load there. So I'll start and call that space A, and then I go clockwise around it. And this becomes B. And then the next one between this force and this force is C, and then the next force. So I'm not lettering the panels of the truss. I'm lettering the spaces between forces. Like if that top force 12 were not there, then there'd only be one space on top, not two. But because it's there, then there's a space there and a space there, and then this becomes another space, E, and then you can see this bottom there are no loads on the bottom chord between the supports, so that's all just one big space. Okay, so we named the spaces first with those letters, and then you name the inner triangles, the interstices here, with numbers. So this is number 1, number 2, number 3, 4, 5, 6, just going across. So we got the exterior with letters and the interior with numbers. Now, the way we'll define members is by both of the letter and the number, or it could be the number and the number. We define it by the symbols on either side of the member. So this member here is B1. This member here is 1, 2. This member up here would be C3. So we name the members. We're going to name the members like that. Okay, and we're going to draw start by drawing the external forces. We'll draw first the external forces, and then we'll draw the forces in the members themselves. So you simply start drawing to scale these forces, and you can, it's best to start with one of them, and the force, just like the other members, is defined by the spaces on either side of it. So this force here, we've got A and we've got B on either side of it. If I cross from here to here, I'm going from A to B. So that force we'll call AB, and it goes from A. So I'll start this as my 0 point, and it goes upward. It's got that's the vector is upward vector by 12. So I can draw it graphically as a straight line up 12 units high, right? So you can even do this on your graph paper if you like. You can follow along and make a little line 12 inches or 12 squares high or something. Then we continue in this direction. So the next one here will be BC, right? This member. And that's going down by 6. So I start at B and I go to C and I go 6 downward. So that's that force. And then I simply continue. The next one is a 12. It goes from C to D. So here was C, and I go down to D, which will be 12. So I do this to scale, obviously, right? And then the next one is 6. That'll be D to E. And so that picks up at D and goes down to E, 6 units. And then we've got one more. This one at the bottom will be from E to A. And that should bring me back, that should close it at A. So here we went from E and we went back up to A. Right? So that closed that figure. The external, and that just simply shows you the external forces are in static equilibrium, right? That it started at A and it came back to A. Okay, so in this case they're all vertical forces, so it doesn't make too much of a diagram there. It's just a straight line. Sometimes you'd have some horizontal forces and it wouldn't be necessarily just straight, but in this case it is. Okay, now the next step, I'm going to graph the members, and I've got the letters to start at. I know where the members will connect to the letters, but I don't know the numbers where this. Well, I have to find the numbers, and the way I do that is I pick two members that will have the same, that will share the same number. So I'm going to try and find this number 1. So if I take this member, this would be A1, and if I take this member, this would be B1. They both share 1, and these, when I'm drawing the forces now, right? These are the forces. The forces will follow the direction of the members. That's the kind of beauty of this thing. Since they're two force members, the axial forces will be in the line of the member. So I can say, all right, let's start with this one, A1. It starts at A, and it goes to 1, wherever that is, and it's horizontal. So I don't know where 1 ends, because I don't know the force that's in A, but I can draw it out as a horizontal, right? And then this one goes from B to 1, and it has this direction. So this is going to also, I don't know how long it is, but I know it goes like that. And those two lines, I know they share this point 1. So there is only one point where those two lines are going to cross, and that is right there. So that in that way I find 1. And knowing 1, I now know the length of this line. And the length of this line, in the same scale as I've drawn the other forces, will be the tensile force in that member. And the length of this line will be the compressive force in that member. All I need to do is measure it, and it gives me that force. So that's the basic procedure. and you just work your way around the truss, and each time you're able to draw a line, you'll know the forces in the member that represents that line. So here's the next field. We can go from 2, okay, A to 2. Well, I don't know where I don't know where 2 is, but I can draw A in this, I'm drawing this line here. A2 would be this horizontal line, right? This will be A2, this line. And then I can go from 1 to 2, since I do have point 1 now, so I know where to start it. It's a vertical, so it's going to go like this. This will be 1, 2. And there is, those two lines that I just drew do have a point in common. They have a point where they cross. It's the same as point 1. So point 1 and point 2 are at the same point. That means the length of this line, the length of 1, 2, is 0, right? Those 2 points are coincident. So the length of that line is 0, so that's going to be a 0 force member. Okay, then we can go on. Let's see, we'll try 3. We can go from C to 3, right? From C to 3. That would be from C, and it's a horizontal. So we draw it horizontally. Okay, so that's going to be our C3. And then I can go from 2 to 3, and that'll have this slope here. So I just take this slope and I copy it the same slope, right? So this has got, this was 8 feet, this was 6 feet, so this is 3 to 4, right? It's a 3, 4, 5 triangle. So this has that same slope, 3 to 4, and I draw it with that slope, and it'll cross C3 at 3, right? That's the point that they'll share. They both share point 3. So now I know where point 3 is, and I know I can measure the length of this line, and I can measure the length of that line, and I'll have those forces. So it continues like this. I guess this is just the rest of it. If you go over here, this will be, D4 will be the mirror image. I'd have initially a D, but I wouldn't know where 4 was. I could go 3, 4, and that would be a straight line. That would take me down. That would give me 4. Then I could look at the, just working around E6. Okay, I know that's going like this. I know it starts at E, and it's going to be a line going up like that. E6 will also cross A6. So that's another, this A has a lot of lines. So 6 again is another 6, and 5 also will be from A and cross 4, 4, 5. So that line, 4, 5. So all these 1, 2, 5, and 6 are all coincident points. And I end up then with this diagram. If the forces and the truss geometry are symmetric, then of course your diagram is going to be symmetric too. So this is then the force diagram. And all I need to do is measure each of these lines, and it would give me the force in the members. You can also get the find the direction of the force. Let's see if I can remember how you do this. You take a free body diagram of it. Okay, this is B1, and A, right? And I think I move in a clockwise direction. So I go like this from B to 1. And then I look up here and I say, okay, here is from B, the start, to 1, the end. I'm going that direction. So that means the vector direction is like that. And if I go from A to 1, or I'm sorry, no, going clockwise, I would go from 1 to A. From 1 to A would be in this direction. Then that force will be like that. So that way I know the sign of those forces. I can also get that. You just have to take like a joint at a time, and well, actually I think you just take the member, and if you follow the crossing of it, it'll tell you. But you have to have it. It helps to have, I mean, you've got to know which end this is going on, so I guess it does help to have a joint. Do it around a joint would be better. Okay, so that's the procedure, and it's pretty simple, and it gives you a graphic plot of all the forces then. And you can, here I just measured them all, and you can compare, I guess I was comparing it to the actual, this is with a little program, this is the Dr. Frame. We haven't used this, have we? Did we use this? Dr. Frame? I'll have to give you a link to it. It's a nice little program. There's a series of them. Dr. Beam is one, and Dr. Frame, and there's a third, oh, Frame 3D. Frame 3D is kind of a mess, but the other two are very, very simple. They're finite element analyses, but you do them kind of graphically. You just draw it and add the forces, and it analyzes it immediately. So for a very quick and simple, so you also take beams and draw shear moment and deflection diagrams and slope diagrams for any beam loading, and they're very simple. So as a quick, handy tool, I'll send you a link to it, and you can have a look. At any rate, that was what this was done with, and it then gives you the forces which match with these. So here are my bottom chord, the A to 1, 2, 3, 4, 5, 6. This is 1, 2, whoops, not 3, 4, 5, 1, 2, 5, 6. So there are all the 16 kip members that I got from that. This one I measured is 20, so that's the side over there in compression. The other side matching it is over here. So that it all does actually give you the correct solution.